And so again, commutative property. In addition and multiplication, the numbers we are operating on can be swapped from their positions. Now, this is a very wordy way of saying A plus B is the exact same thing as B plus A. A plus B is the exact same thing as B plus A. I can change the order of addition and I can change the order of multiplication. And so with this, we also say that AB is equal to BA.
And one of the ways I remember this and keep this in mind is the O in commutative. Commutative is the same as order, right? The order doesn't matter. So commutative, the O in commutative, order, you can switch them around, right? 5 times 4 is the same as 4 times 5, and vice versa.
Now, with this, we're actually going to get sort of a sneak peek, but I want us to turn this into a property of equality. And so what I mean by that is, when we start working with equations, I need us to know that x equals a, so x is equal to some number, is the exact same as a, or that number, being equal to x. Should I switch it off? Switch it off. And so all of these, again, are the same. We can swap sides of the equal sign. We can swap positions or order in addition and subtraction. Or sorry, addition and multiplication. What is not shown here? Subtraction and division. Order is very important in both of those. 6 plus 2 is the same thing as 2 plus 6. 6 divided by 2 is absolutely not the same as 2 divided by 6. Order is important for those other operations. All right, well then why do we care? We care because we're going to be combining like terms today. And so like terms are things that I know we've seen before, but they are specifically terms that contain the same variables raised to the same powers. Terms that have the same variables raised to the same power. And so the sort of shorthand way, the letter and exponent need to match. The letter and the exponent need to match. And so things we might see, 3x and 5x. I'm looking only at the variable. I have x and x. Those are the same letter with the same exponent. These are like terms. Four y and 3y. I've got y to the first. Again, y to the first, same letter, same exponent. Those are like terms. Two x cubed and 4x cubed. Now, I've got x cubed and x cubed. They are the same letter, right? They're both x, same variable. And they have a matching exponent. They both are raised to the third power. Those are like terms. Now, 4xy and 5yx. We got xy here. Ooh, but I have yx here. Well, if we think about the commutative property that we just wrote down, I know that 5yx is actually the same thing as 5xy. right? In multiplication, I can change the order of those two variables. And so, these are like terms. Both have a y, both have an x raised to the first power. Now, if we have something like 2x cubed and 4x squared, we have x and x, which is awesome. But if we look, they have different exponents. The first one's cubed and the second one is squared. Because they are literally not the same value as an exponent, these are not like terms. And last one, 4x cubed and 2y cubed. Again, looking at our variables. Now they have the same exponent, yeah. However, their variables have changed. I have a y and an x. Those are not like terms. Now, with these, I actually want to put a small reminder right down below. This is something we should all 100% know. However, I want to stamp it because it was not part of what we went over when we did definitions. And so if I have 2x cubed, I want us to remember the 2 is our coefficient. The x is our variable. And this 3 is our exponent. Now, exponent synonymous with power, either one. But just really making sure that we know what each of those are, because when we talk about like terms, all of these come up. Once you got this reminder down, flip your notes so that we can see, please. Good. Thank you. Thank you. We're there. We're there. We're there. Far side, we are there. Andre, just make sure your head comes up, please. All right. So, example 1. These two examples are going to be, really fast. Example 1, I've got an expression here with a lot going on. I'm really just looking to simplify or combine my like terms. In order to do that, first thing I'm going to do is really focus on my annotations. I'm going to annotate all of my terms with certain shapes. That's how I do this. And so for 4x, okay, I'm going to put a box around 4x, minus 2x. Okay, well, that's also another x. Plus 2, well, that has no x, so that's going to get a circle. 5x, that's going to be another square. And then negative 7, that's another circle. The reason that I do it like this is that I can visually see what are like terms and what are not. And so if I think about what I can actually simplify and combine, anything with a square or a box around it, I can combine. Anything with a circle around it, I can combine. Anything with a box around it should never be combined with anything with a circle around it. And so the first thing I'm actually going to do is just rewrite this so that my like terms are next to each other. 4x minus 2x plus 5x plus 2 minus 7. Now, notice that for signs, I always take the sign to the left of the value. What that means for our first term, if there is nothing there, assume positive. If there is nothing there, assume positive. If it's negative, you will see a clear negative sign. Once I've lined these up, combining of like terms is actually just performing the operation with your coefficients. And so if I look at this, I'm going to work this left to right. 4x minus 2x. In my head, that's actually just 4 minus 2, which is 2 with the x. Then I have plus 5x. And now over here, this 2 and negative 7, I can also combine those. 2 minus 7 is minus 5. All right, well, one more step. Again, I'm thinking about just dealing with coefficients. 2x plus 5x. Everybody, 2 plus 5 is? So I got 7x minus 5. That would be my final answer. I know that I'm done when I have one of each type of term. I have one x term, the 7x, and one constant term, the negative 5. All right, we're going to jump right to example 2. Now, example 2 has a little bit more going on. However, my approach does not change. I'm going to start with annotations. Okay, I've got so I've got an x squared term. Here's an xy term. Oh, that's just a constant. Another xy term, and there's another x squared term. And so again, I'm going to rewrite this so that anything that's x squared is now next to each other, so things in a box. Anything that's an xy, my circles, next to each other. And the 16 is just going to be along for the ride. What I want you to notice and take away is that right away, 16 does not have another like term, which means that nothing else in this expression will actually interact with the 16. I should, in my final answer, just have a plus 16 just hanging out. And so I'm going to have, 3x squared plus 7x squared plus 2xy minus 4xy plus 16. I've got two sets I can combine, my x squareds and my xy's. Everybody, 3 plus 7 is? 10. Yes, we're going to try this again. 3 plus 7 is? 10. Good. 10x squared. And now, raise your hand, please. What is 2 minus 4? What is 2 minus 4? Gio? Negative 2. So we're going to have minus 2xy plus 16. Again, that plus 16, just hanging out. There's literally nothing I can do with it. All right, I can hear people already starting to do it and already seeing glue sticks happen. That's awesome. That is it for notes. Fold those in half. Get them glued into your notebooks. You got 1 minute. Go. Carol, head up, please.